time to stay. Hey, hey.
Good evening. I'm Sunny Shell, and I'm here with my guest, Bryce. Hey, Bryce.
Hello. How's it going?
It's going pretty good. This is
been a while since I've seen you. So
I know we haven't. It's been a while since we've worked together. I'm really glad that you're on, especially since I'm not feeling really well. So y'all will just have to bear with me. This is the Sunny Spot on Skeptic Haven, where we discuss science, philosophy, and reason from a secular perspective. And I'm really excited tonight because we're going to be discussing the recent pictures that have been taken of our own Milky Way's black hole. I think it's pretty cool. I love black hole stuff. So,
yeah, me too. The black hole, we're talking because I think the Milky Way has numerous black holes, but we're talking specifically the black hole at the center of the galaxy, the big black hole that I'm sure we'll learn a lot more about with the guests that we have on today.
Absolutely. And I'm really excited. I'll go ahead and start bringing in our guests. The first one we've had on before, it's Dr. David. Hi, how are you doing?
Hello, David.
Hi, how are you?
Hey, if you wouldn't mind just reminding our viewers a little bit about yourself.
Sure. So I'm a physics professor, and I actually study black holes.
And so you are based out of Atlanta, correct?
Yes.
Okay. Kennesaw State University. I think I got that right.
Yes.
Very, very good. So you're perfect for the show. The next one we have that's coming on is Dr. Chandra Singh. Hi, Dr. Singh.
Yeah, hello.
And if you would remind our viewers a little bit about yourself as well.
Yeah, at present I'm working in China, mainly the southwest of China. So I'm a research professor in Astronomy Institute of Yunnan University in China. So happy to be here. Yeah.
Very, very cool. Thank you for coming on. And last but certainly not least, Dr. Damien Christian.
Good evening. Hello, Sunny. Thank you. I'm Damian Christian. I'm a physics professor in astronomy, the chair of the physics and astronomy department at Cal State University Northridge, which is in northern Los Angeles. And I got my PhD at the University of Maryland in 1993. David's a fellow Terp, go Terps. And that was on low mass X-ray binaries and black hole candidates, studying them in the X-ray wavelength. More recently, I've been working on the sun and solar flares and things. But black holes are my first love, so to speak, in astronomy. So thank you.
Oh, that's awesome. We may have to have you on again to talk about solar flares then, because that's pretty cool too.
I almost feel like that's the opposite of a black hole. That's like when I think solar flare, I think, and when I think black hole, I think nothing. So
right. True, and there's lots of black holes that we do see some cases where they do flare, right? The accretion disk, get a buildup of energy and magnetic field in the accretion disk, and there are some cases of X-ray flares from black hole systems. So
maybe we should start with the obvious question, just for the layman. What is a black hole? And I'll leave that question open to any of our residents.
You want to go with this, David?
Sure, I'm happy to start, and everyone can put their own. A black hole is a strange object that appeared in the mathematics of the theory of general relativity just a few months after the theory was put together. So Einstein put his equations together, and they had to obey certain rules. And within a few months, someone, under simplified assumptions, was able to derive what space and time are like. Because this is a theory about what space and time is like in regions where there's stuff. There's energy, matter, and energy. It's really technically energy and momentum, stuff moving around that warps space and time. And so a black hole is a strange object that initially people couldn't understand what to make of it because the warping seemed extreme. And this is 1916. And it took a long time for people to recognize that these things probably exist out there in the real world. Einstein never quite believed in them. They were just too strange. And here we are, over 100 years after the theory was put together, and we have these images, two images of these really strange objects.
Are these the first images of black holes?
Yes. So this is the second image. Well, actually, the data was taken at the same time, right? A few years ago, but it took them a long time to process the data for the black hole at the center of our galaxy, and we can discuss why that is.
For some reason, I don't know about you, Sonny, but I guess I just assumed that we had pictures of black holes before now, maybe because of their depiction in science fiction or, nature programs that, posit the existence of them. But I didn't realize that these were actually the first images of any black hole. I thought it was just the first image of the black hole at the center of the galaxy, but this is actually really our first visual confirmation of black holes.
Yeah, maybe we could say that we've had the mathematics there for over 100 years. And so people have played around with the math and have made more and more complicated images from following the math. So we have simulations. And in fact, a lot of our understanding of what we're looking at, if you show the image of this black hole, comes from the simulations.
So I guess my question, and you can interrupt me at any time, Sonny. I know I'm taking over your show, but
You're okay. You're okay.
Fascinating. How big is this black hole, the one that we actually have seen? Like, can we get a sort of relative size comparison? We generally know in our mind how big the Earth is, how big the sun is relative to the Earth. As far as a sun type star, a G type star, what is the size comparison we're talking about here with this black hole?
So this black hole is, so you can imagine a sphere that goes out. If we're thinking of the solar system, imagine a sphere that begins at the center of the sun and goes all the way out to the planet Mercury.
Okay.
Okay, so that's how big how big the event horizon would be.
So much bigger than the sun.
Yes, and the other black hole that's much further away, that was also imaged, that we saw in 2019, would be about centered on the sun. It would be about a sphere that goes all the way out to Pluto.
So
it's the entire solar system.
Yeah, so that's
so much bigger.
Yeah, much bigger. Numerous AUs. I don't know exactly how many, but I know an AU is from the center of the sun to the Earth's orbit.
Right. Yes.
Pluto, we're talking far greater than that. So,
yeah.
Wow, that's kind of unfathomable for me. Like, I don't know why I wouldn't think that it would be that large. And are we talking about something that's just kind of the remnant of a star that has like collapsed in on itself, or exactly? I see Damien shaking his head here, so maybe you can clarify the misconception I have, because in my mind,
Bryce, we should distinguish between stellar mass black holes, which are created when a massive star dies and it explodes and then the core collapses, and they're between sort of 3 and 20 solar masses. We're now in the centers of galaxies. It's very common to have these million to billion solar mass black holes. And so going back 30 years, people know going back to the 1960s, there was a lot of exciting things going on in the galactic center. There were gamma ray bursts. There's lots of supernova remnants. There's lots of radio and X-ray emission. And it was always kind of like the next generation radio telescope. It was like, one of those dolls that you keep opening it and there's another doll inside, right? And finally we realized this thing is very energetic. It's smaller than about 10 astronomical units, 10 Earth sun distances. So it would fit inside the orbit of Saturn, but we didn't really know what a black hole was then, right? As David had said, there's been lots of mathematics and theories for black holes, but observationally, we didn't really understand them in the late 1960s. And then finally, the only thing that this could be that has such a small size and is so energetic is a black hole. And of course, the stars around it, the Sagittarius objects at Andrea Ghez has studied are all zipping around that star. One is in kind of a Neptune-like orbit, and Neptune takes, I think, 160 years to go around the sun. But this black hole is flinging Sagittarius object 16 around itself every 16 years. So there's an incredible amount of gravity there. And of course, David might agree, is when you measure a dynamical mass in the universe, people may not believe your results, but dynamical masses measuring Doppler shifts, I think you can take that to the bank, right? And if you want to pull up a slide, we can show the Andrea Ghez. If you go sort of towards the way we pass all this radio stuff, maybe the 15th slide or so. Keep going, right? Next one. Yeah, let's see if go back one. Yeah. So there, if that's an animated GIF, if you click on it, it should play.
Oh.
Yeah,
Hold on,
maybe it didn't translate well, but you can see that these have been measured in the infrared with the Keck telescope. Of course, you're talking 27,000 light years away, these incredibly faint stars. But each one of those white dots on the right is a measurement, and they got the orbits of these about 24 objects. And in the original 1998 paper, they measured a mass of Sagittarius A star, this supermassive black hole, at about 3 million solar masses. Newer data showed it was closer to 4 million. And so that's pretty exciting because, this is measuring the mass from Kepler's second law, the period squared is the distance cubed. And so, you may be skeptical about string theory or dark energy, but when you measure a dynamical mass, like I said, you can see, we're very confident there's an object there, light can't escape from it, and it's about 4 million solar masses. And what's interesting is M87 in the Virgo cluster is about 1 billion solar masses. So pretty exciting that now we can image it in the radio by combining these signals from all over the Earth, and it's really phenomenal.
So let me slow this down a little bit for some of our laymen, because I don't want to lose anyone. When we're talking about black holes, the black hole itself is not visible and not directly detectable, but we're detecting emissions from it. It emits radiation in the form of X-rays and other type of radiation. Is that what we're actually detecting?
Yeah, I mean, in the stellar mass ones, we see them because there's an accretion disk that's getting heated to millions of degrees as material falls through. So we're seeing sort of the outside of the black hole, and maybe David can explain the EHT images better than I can with this sort of the shadow of the black hole. It's emission around it, and we're sort of modeling this emission. It's basically the diffuse emission around this supermassive black hole that we're seeing, right, David?
Yeah, actually, Chandra's probably better than me at explaining this, but the irony here is that nothing escapes a black hole, yet black holes are the brightest objects of the universe, and that's because when stuff falls in, it approaches the speed of light, and you can sort of think of the stuff as rubbing up against itself, right? So you have a hot gas, a plasma, and you have really strong electric and magnetic fields. You have charged particles that are being ripped apart. You're producing strong electric and magnetic fields, and they produce an enormous amount of energy, and that's what we see. And so you're not seeing the black hole itself, but the stuff that's very close to the black hole that's been heated up to enormous temperatures.
And Chandra, David evoked your name. Did you want to elaborate on that?
Yeah, as you saw in the image just shown, that there are stars going around the Milky Way center. Yes, so these stars are likely to release winds like from the surface, and so the emission that you see in the image is the plasma that is coming from these stars. So these are stellar winds from those stars, which are getting closer to the black hole as a matter falling towards it.
So that's 3 stars orbiting the black hole?
No, it is not. It is the emission of the plasma.
Okay.
So several stars are feeding this black hole. Okay. So as a whole, when this matter falls closer to the black hole, it forms an accretion disk or accretion flow. So this is the image that you are seeing is a part of the accretion flow and the closest possible to the black hole, and it is called as like photon ring, you can say. So it is the last light that could escape from close to the black hole. So it is called a photon ring.
So maybe just to get a sense of scale, Bryce, if you go back to the image that you were looking at before, that Damien was mentioning, right? You saw these orbits. I think it's the one before this, or you were looking there. So on the right, you see all these circles, right? These are a bunch of stars that are all rotating about a point at the center of this image, and you don't see anything there at the center of this image.
Mm-hmm.
There's a dark spot there. It's lit up there. There's a little white dot there. It's Sagittarius A, but there's nothing actually there. And all of these stars can be traced to be orbiting around some dark thing that's at that spot, labeled Sagittarius A. And that's the evidence for the black hole. But now maybe you guys can correct me, but we're talking about, I think the closest star there gets to about 100 times as close as the stuff that you see in the other image of the black hole. So we're much further out there. And so Damien mentioned Kepler's law. You don't need general relativity to evaluate most of those orbits. You can just use Newtonian theory because you're sufficiently far out that you can use just Newtonian gravity. And from that, you can infer the mass of the object that you don't see there, and it's about 4 million times the mass of the sun. The Event Horizon Telescope.
Go to that image of the black hole again, Sonny.
Right.
So
right now we're 100 times closer in.
Gotcha. So what are these bright spots? There's 3 bright, I don't know what you call them, around the halo spots that look a little bit brighter than the rest of the ring. What's going on there?
So I would like to add on this one. So these bright spots are mainly the plasma. Those are moving around the black hole, and sometimes they are moving towards us, and sometimes they are moving away in some sense. So this is like you can say a Doppler boosting. But in this image, compared to the previous one, in M87, which was released in 2019, you could see only one spot. So it was more clear that that was a Doppler boosting in some sense. But here, another problem they faced is the plasma is quite variable in this source. That means the scale in which the source varies is order of minutes, like 4 to 30 minutes. So when they were taking image, it was something like similar to you try to take a picture of a child that was running around the room. Yes. So in some sense, they had to compile these images from different time, and they made a composite image. So, and it is the best fit image. So in that sense, they got this blurry and with this random spot image, because it is a composite image from different instant of time.
Leo Phileas put a comment in the chat that I think he's disputing. I think it was Damien's claim about, or no, it was actually David's claim about the brightest. He says that he thinks that quasars are the brighter objects in the universe. They're powered by rapid acceleration or rapid accretion of material into supermassive black hole, resulting in intense EM emission. Is that correct, David?
Quasars is just a name given to the brightest of these kinds of objects. So when you have a very massive black hole and you have lots of stuff that's falling into them, that's what we call a quasar.
So it's semantics, basically. It's the same thing via another name.
Yeah. So what we try to do is to understand all of the different kinds of objects that basically have a giant black hole and stuff falling into them. So we see different kinds of objects. The M87 black hole, for example, is different from the one in our galaxy in one clear way. First of all, there's more stuff falling into it. And 2, it has a beam of energy called a jet that's coming out from the center. So near the black hole, something's happening that's not happening in our galaxy. That's not happening around our black hole. So the question is, why is there this enormous jet that basically involves fast-moving things being thrown out of the galaxy from the black hole? And that's happening in M87, but it's not happening in our galaxy around our
Where
black
is
hole.
M87 is the designation of a different galaxy?
Yes, it's just it's the name of a catalog.
Okay.
There's a name, but it's a much bigger galaxy, a different kind of galaxy. We live in a sort of flat disk-like galaxy, so we can talk about how the different galaxies form. M87 is a spherical, elliptical galaxy, and there's a much bigger black hole at the center there, and it has this enormous jet.
How far away is it?
It's like 50-something million.
Yeah, I just Googled it. It's 54 million light years away.
And how are we able to observe?
It's because that black hole is so massive. Its even horizon is 3 times larger, so it has a bigger angular size than even the one in the Milky Way. So we get lucky that it's such a, I think it's a million. What do they say, David or Chandra? A billion solar masses from 87 or 3 billion.
Yeah, so M87, black hole in M87 star is around 1500 times massive than Sagittarius A star.
Okay.
And it is located something around 2000 times farther compared to Sagittarius A star.
So upwards of 6 billion solar masses.
It is 6.5. 6.5 billion solar mass. And
so since I was in graduate school 400 years ago, the mass has gone up for M87. It's inflation.
Yeah. Maybe we should point out that, the M87 black hole, these black holes are among the biggest observed black holes at the centers of galaxies. I think there are a handful that are now at 10 billion solar masses. Yet that is completely negligible in terms of size compared to the galaxies in which they live. So somebody once pointed out that if we take a black hole the size of the M87 black hole and we put it at the center of the Milky Way, so we imagine the Milky Way is kind of like the size of the United States. It's a flat disk-like galaxy, the size of the United States. Then the M87 black hole would be no bigger than about the size of a marble placed at the center of the United States, right? Somewhere there in Kansas. So it's completely negligible size-wise.
Chandra, is there a black hole at the center of every known galaxy, or do we have reason to believe that there is one?
Yeah, it has been mostly found that there is a black hole at almost most of the galaxies, at the center of most of the galaxies, yes.
Do we know why?
Because I think in some sense black holes they are themselves the end products, but they are also leading to formation processes in the universe. So the matter that is ejected from black hole in the surroundings of black hole, they are also a precursor for star formation. So you can say a black hole is a recycle bin for the universe or every galaxy. So
does that mean that these black holes predate the existence of all of the other matter and material in the galaxies that they're at the center of?
I think I will not be able to answer this, but maybe Damien or David can answer.
Well, the reason I'm asking is because it seems to me that if there's a black hole at the center of each galaxy and they are ejecting material that is the basis of star formation, it seems to me that they are the reason why there are stars in these galaxies in the first place, and without them there would be no stars. Am I way off base?
I don't think all over the galaxies, but in some sense, yes. I mean, they are contributing in some sense, but not for everything that is happening.
Okay, gotcha. So they're go ahead, Sunny.
I was just going to say, for a minute, I thought we had solved the Coulomb cosmological argument right there. First cause was the black holes.
Yeah. By the way,
basic question here. Sorry.
No, go ahead.
No, go ahead. You were saying, by the way, something.
I was just going to take a moment to acknowledge the people who are participating in the chat. I already mentioned Leo Filius, Aaron Coalson. We've got Kat, the humanist, back there. Who else? Theoretically. By the way, if you guys have questions for our astrophysicist besides the one I was asked, please do so. Farron Salas. Cool. I appreciate you guys. Okay, go ahead, David. I'm sorry.
I was just going to say that you asked a very fundamental question, which is still unanswered. So black holes form and galaxies form, but do we really know that galaxies form first and then black holes, or do sort of black holes tend to form first and then around them the galaxy forms?
That's what I was pretty much wondering.
Right. So we don't really have the answer to that, and that's one of the things that we're working on.
But there's also black holes that form that are not in the center of galaxies.
Yes.
So
I think that was the other type of black hole that Damien was talking about.
Yeah, the stellar mass black holes that come from stellar evolution. So, and then there's the third type that are sort of intermediate mass that maybe 10,000 to 100,000 times the mass of the sun. So they're more massive than the stellar mass black holes, but not as massive as the center of the black holes and centers of galaxies. And these are really hard to explain because we don't really have a good model for, you can merge a whole bunch of small black holes, but you need dozens of mergers to get up to 100,000 times the mass of the sun. So in our paper with David and Chandra, I think in 2016, we tried to address this problem by invoking mergers of, if somehow a supermassive star makes a 100 solar mass black hole and you merge that 7 times, you get 10,000 solar masses, and then maybe you merge some of those, you could get up to 100,000 solar masses. So, one of the exciting things in the last 20 years with the Chandra X-ray Observatory and XMM Newton, we've detected what are called intermediate mass black holes, and they're sort of a different type that are in between. So I should have revised my slide and make it 3 types of black holes. Stellar mass, which are say 3 to 20 times the mass of the sun, intermediate mass 10,000 to 100,000, then supermassive over 1 million, say. So, anything to add there, Chandra? I didn't realize we're co-authors and we've never met before. It's really funny.
No, I just wanted to add about the difference that David pointed out about M87 and our Milky Way center. Is that M87 is the case where the matter was accreting at higher rate, while our Milky Way center is like a starving black hole. So the rate of infalling matter is quite small in case of our Milky Way center. So I just missed to add before, so I wanted to add.
And that should add to what Chandra just said, that the question that we got about quasars, those have matter falling into them at a rate that's much, much larger than M87. So there's a whole range of what's called accretion rates onto black holes. M87 isn't very large, but it's a lot larger than our Milky Way.
So we have a couple questions from the audience. Skeptic Haven asks, how did they take a picture of this black hole if our telescopes can't do it? Y'all don't jump on it all at once now.
So who wants to take that one?
You want to take that? You had some nice slides on that.
Oh, okay. Let me add that. Do you know which? Maybe observing. I don't know which one of those did you want me to show?
Yeah, I think if you go to one more slide, go back one. So we combine signals from radio. So the resolution of a telescope is determined by the wavelength over the size of the telescope, and so in the radio you're kind of already have poor resolution because radio waves are so long. They're a centimeter to meters. But if you can combine signals doing something called radio interferometry, you can put your radio telescopes far apart. And then on the left there, you can see a little squiggly. If you combine constructive interference, you can sort of amplify the signal, and you don't get more light gathering power, but you get a lot more resolution. And so if you go ahead a slide, there's Sunny. You can see for years we've had the very large array. It was in contact with Jodie Foster, and these antennae are on railroad tracks, and you can move them far apart and combine all their signals and have an effective telescope, the resolution of a 36-kilometer telescope. And then with modern computing and the internet, we can now take these telescopes and put them in all different places around the Earth, and then combine the signals and get an effective telescope that has a diameter of 3,000 kilometers up to 10,000. The EHD, Event Horizon Telescope, with this new image is about 10,000 kilometers effective area or effective size of the telescope. So it has 50 micro arc second resolution, which is really amazing. So we can sort of zero in on the black hole in the center of our galaxy in M87. And as David and Chandra mentioned earlier, it's been, there's the VLBI, very long baseline interferometry, where we're adding signals from thousands of kilometers apart to try to image the plasma around these black holes. And so, we're lucky in a sense that the Milky Way black hole isn't very active, or, we wouldn't be here because it would make a lot of gamma rays and X-rays. But on the other hand, it has just enough emission to light it up so we can see it with radio interferometry. Thanks.
And before we get to the next question, since you just brought it up, Damien, a little while ago, I can remember watching Contact in the movie theaters back in the day. I think I was still in high school when that movie came out, but I had this sort of idea in my head that the Very Large Array was meant to find aliens, but apparently that's not really what it's used for. It's for finding black holes. Am I right?
Well, it does lots and lots of different research projects, star formation and galaxies and stars. And so I think one of the, there's a new submillimeter array in the Atacama Desert called ALMA, which is at sort of a few millimeters, and it zeroes in on star formation. And so that's one of the new exciting radio windows that we have to look at young stellar objects with possibly planets. And they have cold disks around them, not like the hot accretion disks we're talking about here for black holes. But the VLA has been an amazing workhorse for astronomy for, 40 years now. I forget when it was first built, but so.
And we also have another question from the audience.
Can I add something?
Oh yes, please do.
So because the previous question, when people think about observing some astronomical object, they might think that maybe in what we can see with our eyes, yes. So those are like optical wavelengths or in a visible range. But if you think about our Milky Way center, there is so much dust and so much things on the way, like in between us and the Milky Way center, that you cannot deal with that using a visible range, or optical telescope. So the most suitable scenario is using the radio telescope, which can resolve the closest possible region around those black holes. So that's why it has been used. So because we cannot do with the usual optical ones. And I would like to add that there has been a network of telescopes, radio telescopes, which were spread around the world from northern hemisphere to southern hemisphere. And there were total 8 radio telescope network, and they effectively made a baseline equivalent to the size of the Earth. So it was possible to resolve that region because the resolution depends inversely on the separation of this baseline. So the bigger the baseline, the more resolution you achieve. So it was possible to, in a sense, image this black hole center, Milky Way center. And I would like to add that this is something like a model dependent case. So what they do is you have different data from these telescopes, and they manage to develop a software which can reconstruct this image in this obtained from radio telescope. And so on the other hand, they use the simulations. That means they solve set of equations governing the matter going around these black holes, and they try to optimize this scenario, get the results from simulations and get the results from observation and try to find the best fit. So in some sense, it is in a way a model dependent case. So if you try out a different scenario, you might get a different answer. So just before this image was released on May 12, there was a paper on May 10 by Japanese researchers, and they claim that the image that has been produced by Event Horizon Telescope collaboration may not be correct or may be biased. So this is still, we have to be careful when we say this is the image, okay, because this is means the image with the most broad consensus in scientific community. I don't say this is the image.
Sorry, I was muted. If I'm understanding you correctly, the image that we're seeing, it's not really an image so much as a simulated image. Is that correct?
So one thing is that you can notice that this image is blurry, yes. So the problem is the resolution we can achieve with radio telescope. So it cannot give us as sharp image from as we get from simulation. In simulations, you can control the resolution you want to achieve. So the results that they obtained from simulations were really fine and quite highly resolved. But they have to make the simulation results blurry enough to be comparable to this blurry observed image. So in some sense, they try to find the compatibility between these two, and then they conclude, okay, this is the result we have. And the main conclusion came from this size of this photon ring, because from general relativity there is a prediction what is the angular size of this photon ring, and that gives you the estimate of the mass. So they could confirm the estimate of the mass to be around 4 million solar mass, which were also obtained from previous observation, which were not done by these people, but they all came to the same conclusion. And till now, we don't have any estimate of spin, because from simulations, you have so many sets of combination of different parameters that they could not really conclude about the spin of the black hole, because astrophysical black holes have mainly two parameters, the mass and the spin. You don't have any other information that you want to discover, because you cannot get any other information about it. So from this observation, they got only the mass, and the spin, in case of spin, they concluded, okay, this has to be non-zero, because the simulations with non-zero spin gave them this compatible result. Okay, so the spin can be anything from 0.5 to 0.9 or something in that range. So there is always an option of deviating away from these assumptions. So we need more findings to.
So we do have other questions in the chat, but before we get to the next one, because we were about to put it up, but I want to ask a question that I think precedes this question. And Damien mentioned the different kinds of black holes. With the two that we're talking about here, do we have any idea what caused these black holes in the first place? Is there any way to even investigate that? Are there any theories or models behind this type of black hole formation?
The basic picture seems to be a combination of two things. Galaxies merge, they come together, and so you have some smaller black hole at the center, and the black holes come together and they get bigger. But stuff also falls in toward the center of the galaxy, of the new galaxy, and accretes onto the black hole, and that also builds the mass of the black hole. But this combination, as Damien was mentioning before, of merging and accreting, doesn't seem to be able to really account for some extremely massive black holes that we observe very early on in the universe. How did they get that big? So we can estimate. So when black holes are feeding, they generate this energy that kind of is like saying, stop feeding me. They push stuff out. And so you can only add stuff to the black hole at a certain rate, not faster. And so there's some tension here between how these black holes, these quasars, as the person mentioned earlier, that we see very early on in the universe, just a few 100 million years after the Big Bang, we see black holes about as big as M87. How did they get that big if the rate at which stuff falls in is limited and you don't have that many mergers? Right? We can sort of estimate these parameters, and so there's some tension there.
And I think Farron's question may have been answered, but I think he's probably talking specifically about the more common type of black holes there, wants to know what causes them to collapse in on themselves. So I think this is in reference to the black holes that are the remnants of dead stars. So did you want to take that one, Damien?
Well, yeah, I mean, basically, when our sun cannot turn into a black hole. It's not massive enough, but say a really hot star called an O star over, say, 20 solar masses, at the end of its life, it'll fuse helium and hydrogen all the way up to iron. And when it gets to iron, that iron core will collapse. And there's a couple different ways to do this. But once that iron core gets over 3 solar masses, there's no known force in the universe. It's basically gravity wins. Gravity squeezes that down to a singularity where not even light can escape. And so often massive stars may make something between 1.4 and 3 solar masses called a neutron star, which is basically all the free electrons and all the free protons combined to make neutrons. And that's like a neutron soup. Those things, it's basically you've squeezed the star down to the size of a city, let's say a radius of 10 kilometers. But if that star had even more mass, you can push it so that now it's over 3 solar masses. No known force can stop that. Not even light can escape, and that's a black hole. And there's another scenario where this massive star, you have a supernova, which is a hypernova that is so massive when it explodes, it collapses directly into a black hole. And Chandra and David may know more about hypernovas than I do, but it's sort of exciting in the sense we've tried to look for these stellar mass black holes in the Milky Way since the early 1970s, and we found maybe 24, whereas now we look in all these different active galaxies and we find supermassive black holes in their center. So the friendly competition between people who study stars and people who study galaxies, we've only found about 24 stellar mass black holes in the Milky Way galaxy, whereas most galaxies seem to have supermassive black holes in their center. So
maybe someone can help me understand. Go ahead, Sunny. I think you wanted to add something.
No, I was just waiting to do the next one. I think this is a great discussion. Go ahead.
Yeah, we're going to get to Leo Phillies has another question in a moment, but I have grown up hearing and believing and recognizing that a black hole is not even light can escape. I think everybody has heard that, but certain types of radiation does escape in order, like we can detect. You talked about the emissions that a lot of them emit. So how is it that certain types of radiation can escape but light cannot? What makes the type of radiation that can escape the gravity of a black hole different than visible light radiation?
It's just that it's coming from further out. So if you're not that close in, you won't get dragged in, right? So if you cross the event horizon, nothing's going to get out, neither light, no matter.
Okay.
You have to be further out, and the stuff that's falling in is the light that escapes is escaping from outside of the event horizon.
Got it.
There is no radiation that's coming to us from inside of the event horizon.
Okay, that is helpful. That clears up a lot because that was a misunderstanding I had for a while. And Leo Phileas has another question here and wants to know what the three of you think of Fermi bubbles and the possibility of activity in Sagittarius A past. And you guys may have to dumb that down for the rest of us because I have no idea what that is.
So Sonny, in one of the sorry, Bryce, one of the last slides, we have a picture of the Fermi bubble. It was discovered in 2010. You have to go another slide forward. There. So the data from the gamma ray observatories in the upper left, and then the model with the jet that David was talking about. And of course, David is a jet expert, and Chandra too. So it seems that probably billions of years ago, the black hole in the center of the Milky Way was active. It was getting material dumped on it, and it was spinning rapidly and making gamma ray emission that left this imprint, what's called the Fermi bubble, which you can see, I think it extends a total of about 50,000 light years from top to bottom across sort of the plane of the Milky Way. And so then the artist's conception in the lower right sort of shows how it may have formed with gamma ray emission from the active phase of our Sagittarius A star back probably a couple billion years ago. So Chandra and David might want to elaborate. But it was very exciting when this came out. People were really excited because I think at the time, the gamma ray observatories were, I'm not sure when the Fermi, it was a satellite in low Earth orbit, and I'm not sure when it sort of stopped working, but it was, I think, near the end of its lifetime. So.
And Richard Matson has a question as well. I
So
think he started off.
Can I add few things?
Oh, yeah, please.
So Damian mentioned about stellar mass black holes. There are around 20 stellar mass black holes in our galaxy or in another galaxy which have been studied. So according to one estimate, there are like around 100 million stellar mass black holes in our own galaxy. So you can see that how much discovery is remaining. Yes? So we have discovered in only orders of tens, but there are in order of millions.
So we've only looked this far away from us, and the distance we're talking about is from where I am to where you are. But we've only actually looked this far.
Even if you focus in our own galaxy, there is a huge number of black holes yet to be discovered. So I think in future we will have more observations and more discoveries in this sense. And about Fermi bubble, I would like to add that this can be some kind of remnant of past activity of our Milky Way center black hole, because now our black hole in the Milky Way center is starving. Maybe in the past it was accreting, or the matters were falling at more rapid speed or rapid rate than now. And somehow this jet was emitted in those time, and that left a mark on this in this gamma regime. And so what we observe now is maybe the remnant of past activities that our Milky Way center might have.
I'd like to mention another mystery that we're trying to understand, which is
what was that, David? I'm sorry.
I just wanted to connect to what Chandra just said, which is that there's another mystery that connects black holes and their galaxies, which is that in every galaxy in which we can make measurements, when we measure the mass of the black hole and we measure sort of random speeds of stars in the galaxy that are just too far from the black hole to feel the black hole's presence, there's a connection between them. In every galaxy where we can measure this, there's a connection. And so somehow this is telling us, we think, that when galaxies form, black holes form, and they sort of tell stars something about their presence in some way, perhaps during the phase when they're active. They spit out energy, and there's more energy the bigger the black hole is, and they can communicate to the rest of the galaxy that there's a big black hole there. And somehow these stars start to move around in a way that's connected to these black holes.
Are you saying that the stars tell us about the presence of the black hole, or the black hole tells us?
Okay.
Both.
If you measure something about the stars, you can say, oh, I can tell you something about the black hole at the center of that galaxy. And if you measure the mass of the black hole in a galaxy, you can say, oh, I know something about the stars very far away from the black hole, what they're doing. And you'll find that, in fact, they're connected in that way. So what's the connection? Are they
connected in the sense that the stars are caught in the black hole's orbit by gravity?
All. That's the mystery. The stars cannot feel the black hole's gravity. So how is this connection generated? And the one possibility is that it's generated during active phases. So in our galaxy, stars that are sort of too far away from the black hole to feel the gravity of the black hole are moving in a way that's connected to the 4 million solar masses at the center of the galaxy. Right? So how did that happen?
I mean, this is more of a question that I don't know if anyone has the answer to, but is it possible that there's another fundamental force that we don't know about that is connecting them, or could it be some invisible stuff like the what are we calling it?
The dark matter?
Dark energy or dark matter or have we eliminated all of those possibilities and we're just calling it a mystery for now?
If you look at the list of papers that have been published, yes. So one of the papers dealt with different kind of candidates for this compact object in the center of Milky Way. And so there were several candidates like boson star or naked singularity or different kind of space-time curvature in the representing the compact object in the Milky Way center. And then they concluded that the best possible scenario is the space-time metric, which describes a rotating black hole. So in that sense, they excluded these possibilities in this recent work by EST collaborations.
So, Sunny, you're muted, but
Sorry.
Yeah.
Well, you kind of made me think of something that actually another. I'll get to Richard's question in just a second, but it kind of made me. Aaron's question is kind of what popped up for me and what I've been wondering about, and that is, what are the practical applications that this new data could have here on Earth, if any? I see smiles. Y'all are smiling.
Yeah. What are the implications of this?
So one thing, so whenever these kind of efforts are made, you need to develop some kind of technologies. Yes, like for example, instrumentation is one of the developments that happen in this process. So because we need to coordinate all these telescopes, we need to refine our data. So I think one of the implications of this work is our society can benefit from the instrument development and the software development coming from these works. Other than also another issue is that we are always trying to find this fundamental question of means where we are and what is this our surroundings, what is our place in the universe. So we are trying to address this fundamental question about these basic ingredients of nature. So yeah.
That is a brilliant answer, and one that never really even occurred to me to think. I don't think this answer occurs to a lot of people. Just the simple fact of discovering something compels us to want to learn more, which compels us to create the tools necessary for us to gain that sort of knowledge. And these tools can be used in all sorts of practical ways to learn more information. Space age technology, a lot of things that we use in our everyday lives came from a desire to explore space in the first place. Space age metals, I'm sure a lot of the computer technology that we're using. And so it benefits us in ways that we don't even think about, that may not even be related to space. But that's a great answer. I appreciate that.
Yeah, can I just add, Bryce?
Mm-hmm.
Sorry, go ahead.
That in the 90s, when Hubble was out of focus and they developed software to try to correct the images, some of that software was used to search through mammograms to look for early signs of breast cancer. So there's, we don't know what the spin-offs of the EHT might be, but as Chandra mentioned, there's, this is a new technology in a new era, and it's really exciting if we can have the resolution of a 10,000 kilometer radio telescope. I mean, it's, when I was in graduate school 400 years ago, we talked about sort of milli-arc second resolution. Now you're talking micro arc second, 1 million times better than an arc second. So it's pretty exciting.
Okay, now to Richard Matson's question. His first question, the first part of it was more of a comment. The actual question part, why are we seeing an oval and not a straight line? And I'm assuming I'm not sure if he's referring to the bubble that we were looking at or the actual image of the Milky Way or the black hole. But so maybe he needs to elaborate. Which image were you talking about, Richard? Unless one of you cares to guess.
My impression is that he's talking about the Fermi bubble.
Right, that's what I was thinking.
Why is that not in the form of a jet? And the idea is that if there was a jet that produced that, it was a long time ago, some billions of years ago, and so that energy has sort of spread out and diffused.
Now that brings up another good question. The images that we're actually looking at, are they he was talking about the black hole, and I'll let you guys answer that. But just this applies to black holes as well. These images that we're looking at, they're not as they exist today, right? We're looking at a long time ago, correct?
Yes.
Okay.
26,000 years ago for the black hole in our galaxy, and 53 or so million years ago for the other one.
So can I add about the Fermi bubble? Like one can imagine a boat going on the water surface, yes? So when the boat is moving, it is displacing something on the surface, and it takes a shape which you can imagine like what the Fermi bubble is having, yes? Because when the jet moves, it is going to displace the matter around. So the jet is not only the component. You usually have a cocoon, because the jet is going to mix with the surrounding while it is moving around. So, and then this expansion happens, which is going to lead to this kind of shape in some sense.
I brought that image back in because on the bottom, that kind of shows what you're talking about. Is that's what you were kind of talking about.
Yeah. So no, I mean to say the shape. I think the question was about the shape they got. Yes. So it is something like, because the jet has to, in some sense, it has to push through the matter in the surrounding. So it is going to displace, and the jet itself is going to mix with also the surrounding material. So in that process, it is going to form this kind of shape.
What is the actual physical shape of a black hole? Is it spherical?
Yeah, I think that is the most optimum. Even if, according to some theory, if it has any irregular shape, it is going to achieve that, in some sense, that the perfect sphere that you can imagine. Yeah.
So the image that we saw, I'm not positive that you guys have seen this movie, but I imagine that most of you would have seen Interstellar. I'm told I've been told by non-scientists that that's the most realistic depiction of a black hole that has been rendered in a film. And now I have the opportunity to ask some actual astrophysicists whether that is the case or not.
I think what you're talking about there is the result of a simulation of material that's rotating around the black hole, and that you're seeing edge on. So here is the plane of rotation of this material. And if that's the case, and the black hole is in the middle here, and this material is rotating around the black hole, what you'll get, because of the strange effect of the black hole on space and time, is that you'll see the back, you'll see the stuff that's in the back, behind the black hole, hiding behind the black hole. You'll still see that light. That stuff is hot as well, and you'll see that despite the fact that the black hole is in the way, because the black hole curves space. And so that light is generated and curves around the black hole. And so you see the light in the front, and you see the back material as well. And that's true above and below. And that's the image that I think you're talking about. And so one of the interesting questions is, that's not the image that we see when we look at the black hole in our galaxy. Why is that? That's what we would expect to see. If this galaxy hasn't been doing much for such a long time, then everything should be sort of rotating in the same direction. And so the stuff we would expect to see an image like that, where the black hole, we're looking at it edge on. The stuff near the black hole is rotating in the same plane as everything else in the galaxy. And so we should see something like that. But that's not what we see. Instead, we see something that looks more like the rotation is like this. And everything else in the galaxy is rotating like this, roughly speaking, whereas near the black hole, the stuff is rotating like this. That's the kind of thing we're looking at. And that's kind of surprising. Why is it that near the black hole, the stuff is rotating in a different plane? That's hinting at something about the history of our galaxy. It interacted in some way with some other stuff, neighboring galaxies or something like that. And it's kind of a surprise.
Okay. Can I add something?
Yes.
So in the movie Interstellar, the main scientific advisor was Kip Thorne, the Nobel laureate himself. So in that movie, the simulation results they took is about a thin accretion flow. So that means the flow was mainly confined in the plane, equatorial plane. And so the modeling was done based on a cold accretion disk, which is thin in shape. But if you think about M87 and Sagittarius A star, in that case, the flow is hot, in the sense that the accretion rate or the inflow rate is not so high. So the accretion in these cases, which EST collaboration has produced, these are coming from the quasi-spherical hot flow. So this is completely different than what Interstellar movie showed.
Okay. And we have one final. Do we want to get to the final question, Sonny? It's also from Richard Matson. When you say that they are connected to the black holes, and he's referring to your comment, David, where the stars are connected somehow to the black holes, but not via the force of gravity. He wants to know, is this connection material? And I'm not sure who that person is, but is it a material connection, or is it a, like, in what way, what type of connection are we talking about? Maybe
we're talking about direct physical connection. So specifically, so there are different kinds of connections, but a very strong correlation is found between the value of the mass of the black hole. All right, so 4.6 million solar masses in our galaxy, 6.5 billion solar masses, M87, and we have many more of these measurements. And then the stars, the random speeds of stars that can't feel the black hole. So in our galaxy, the random speeds of stars out here is has some value. And then in M87, you can be sure that those random speeds are larger.
So we're talking a correlation then.
Yes, there's a correlation.
Not when you said connection, you're talking about a correlation of the speed of stars relative to the black hole.
Yeah, we found a correlation, and then the question is, what's the connection? What's the physics behind that correlation?
And we don't know that, right?
And we don't have an answer to that.
Cool. Well, we've gone an hour. I did have one question before we close, and this is kind of indirectly related. Is Star Trek V: The Final Frontier a bad movie? That's for everybody.
I'm not a fan of science fiction, so I don't know.
Haven't seen it yet.
That is surprising to me. How about you, Chandra?
No, I'm not aware of what is the storyline of Star Trek.
That's amazing to me. For some reason, I would have just assumed that every person who is an astrophysicist who is under the age of 60 was inspired in some way by Star Trek and then became obsessed with it and then saw everything related to it and then devoted their lives to astrophysics. But apparently my bias, that is an incorrect assumption.
In my case, I was inspired by the actual programs on astronomy. So it was not fiction one. I was inspired by actual discussion on astronomy. Because of course, I agree the fiction can lead to some creativity, but that really didn't work in my case.
And apparently not in your case either, David. You're not a science fiction fan.
Science fiction always kind of annoyed me, actually.
Okay. Well, Damien is giving me the Vulcan salute. So, do you have any idea what I'm talking about, Damien?
Yeah, totally. I mean, it's pretty exciting. And when you look at there was only 3 years of the original Star Trek in the '60s, but what they did was amazing. I mean, they just had such great ideas. And Gene Roddenberry, it's really genius when you look back. And I'll definitely see the new one, but I haven't gotten to it. So,
the reason I asked about Star Trek V, for anyone who's watching and who's a nerd, the plot of that movie has them taking the Enterprise into the center of the galaxy. I think most people consider it to be the worst Star Trek movie, but they take the Enterprise into the center of the galaxy and they meet God there, but it turns out to not be God and it's an alien, and it's kind of ridiculous. So it was more of a tongue-in-cheek sort of, rhetorical question, if anything else. But go ahead, Sonny.
I was just going to say I haven't watched that one, but I am a mad Star Trek fan, and I'm watching all of the new Paramount Plus streamed shows with that. So I'm devastated that you guys are not Star Trek fans.
Well, we got Damien.
Totally, so. Totally devastated. But I do want to thank all of you guys for coming on. I do want to get your final thoughts on black holes on our topic today. And we'll just kind of go around. David, if you want to start with your final comments.
Sure. I'll just point out maybe that there's an interesting philosophy of science question here lurking behind everything that we've talked about, which is that, without theory, without a model, we couldn't say anything about this image. So you really need you can't just look at the world in strange exotic places and say, oh, this is what we're seeing. You really need models, theory to sort of help you understand. And this is what Chandra was mentioning before, that all of these things, these conclusions are model dependent. And so this sort of speaks to this idea of trying to understand whether a theory is right or wrong. But you can't just do an experiment or make an observation and say, oh, the theory is right or the theory is wrong. They're much more interconnected.
Great final comment. Chandra Singh, if you want to give your final comments.
Yeah, I would like to add that we have shared some links in our description of the channel or the video, and it will be nice that if people can go to those websites if they want to have some reliable source of information, then they can get more insights into this. And of course, studying the scientific paper might be too technical, but somehow they can get some sense that, okay, so these are the simulations versus the observation. So we are just trying to cross-verify in some sense that, okay, which is the most appropriate scenario here. Thanks.
Thank you. Thank you so much. And Damien, you get the final word.
Thank you, Sunny and Bryce, and thanks for having me. I just think that people want some background on discovering the black hole in the center of the Milky Way. There's a great Nova special called Monster in the Milky Way featuring Andrea Ghez from UCLA, and that could give people some background. But I always think of black holes as just sort of physics, where now you've made something so dense and so compact that, you know, not even light can escape. And I don't, you know, science fiction has really taken and run off with black holes and wormholes. You go in here, you come out somewhere else in the universe, and, you know, in an Einstein-Rosen bridge or something. And I don't really believe that. I just think they're super massive and super dense. But it's exciting. As I said earlier, we now have radio telescopes with, you know, 1/1,000,000th of an arc-second resolution. You go out in the night sky with your little telescope, you're talking an arc-second resolution, right? So we really are pushing the boundaries, and it just shows how much more we need more X-ray telescopes. We need more radio telescopes because we can really start imaging other systems. So thank you.
Absolutely. And in order to do that, we need to get out and vote for candidates that believe in science and are willing to promote science and fund science. So it's getting really, you know, a lot of places have their midterms. So I wanted to go ahead and get that out. Bryce, I wanted to really thank you because I am super sick. And you allowed me just to sit here and listen and be a geek, and you took over, and I really do appreciate it. And last minute, y'all, he got word to come and help me like 5 minutes. So,
yeah, I was literally walking in the door like right before the show started. So, but it was all good. Black holes, I'm very interested in. I am a huge science fiction fan. I'm also a science fact fan. So this was a treat for me. And also, I do want to invite the three of you, if you would just stay a few moments after the show to meet us backstage after the credits.
Yes, absolutely.
Thank you for having me.
Absolutely. And for all of you in the audience, if you really enjoy this type of content, please be sure to share, like, and subscribe. As you know, we are revamping all of our programming. So we are now the Skeptic Haven, and this is now the Sunny Spot. But we still have all of our great content. We have the Secular Soapbox, Women Atheist Unloaded, Sandbox Debates, One Good Reason, and The Bible Says What. If you really want to help us, consider joining our Patreon account. Every little bit helps. And I want to thank everyone behind the scenes, Wes, Phil, Kat, and Jena, and especially you, Bryce. You really came in for me today. I owe you. And for everyone else, please join us again. And until next time, remember to think critically. Good night, everybody.
It's a sunny day, we got some time to stay. Hey, 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 and everything's okay. It's a sunny day, we got some time to stay. Hey, 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 and everything's okay. Hey. Hot sun, the rain's gone, we gotta have a lot of fun. All that's over gone, a smiling face for everyone. Life can be so beautiful when you stop your judging. Just be